today we're continuing with our frequently asked questions from ZIMSEC and Cambridge. So today I identified two questions that I think are very common. So they are on scale and similarity. Okay. So the two questions, the reason I identified them was they're kind of interrelated. So the first one, it says two similar cups have diameters. You're given these diameters and you're asked to write down the ratio of their volumes. Okay, also called the volume factor, the volume ratio factor. And then here you're given that the volume of the smaller cup is 100 cubic centimeters. Calculate the volume of the larger cup. Okay, you're now applying proportion. But the way that you derive this question HN says a map is drawn to the scale 1:80,000. Calculate the length of a line in centimeters on a scale which represents 5.6 kilometers. Okay, this question now asks calculate the actual area in square kilometers represented by the map represented on the map by an area of 100 square centimeters. Okay, so all those two aspects, they're kind of related. They kind of come from the similar topic called similarity. So similarity, let's say I want to build a house. This house, I can come up with something called a model for this house. Okay, just giving you some of the practical aspects here. So the model for the house, it means that it has corresponding measurements. Okay, there is it's similar. A model is similar to the real structure. Okay, so if let's say you want to build a house, then you would expect that the model is similar. It's similar in what way? It's similar in measurements. So when we talk about similarity, we mean that similarity, it's a concept that we use in maths. When we say something is similar, we mean that the ratio of the corresponding sides is constant. Okay, it's actually similarity. Okay, so this was supposed to read similarity. Now you know by now, I think, that I'm very lousy at spellings. So this was supposed to read similarity. So two conditions: the ratio of the corresponding sides is constant, the angles are the same. Okay, so when we say something is A similar to B, we mean that the ratio of the corresponding sides is constant, and also if there are any angles, the angles are the same. So here the angles that I mean, I actually mean the corresponding angles. The corresponding angles are the same. So you can have, let's say this is a square. Okay, so this square is similar to this square. Very lovely drawing, but then I'm sure you get the sense. So it's similar in what regard? The ratio of the sides is the same, since all the sides are equal and all the sides are equal, and also the angles are also the same. So just an air of caution here. When we say the angles are the same, we don't mean that all the angles they are the same. We mean the corresponding angles. Okay, so for example, if we say that this is similar to this in the way that I have drawn here, what it simply means is that this angle and this angle, they are the same. This angle and this angle, they are the same. They don't need to be necessarily all the same. Okay, it's not the angles of themselves which are equal. It's the corresponding angles. Okay, so this is what we mean by similarity. Similarity in two aspects. Similarity with respect to sides. Okay, the ratio of the corresponding sides. So normally when you're asked any questions on similarity, you're supposed to identify the corresponding sides. If you take the ratio of any of the two corresponding sides, sometimes you can read by inspection, you'll be able to inspect which angles are equal and also which sides would be equal in that regard. And then when you take that ratio now, that ratio you can apply to any sides of the two similar shapes. Okay, so this is what we're talking about. We're talking about corresponding sides, and we're also talking about corresponding angles. When these two are the same, then we mean, or when these two conditions are satisfied, then we are talking of similarity. Okay, as opposed to congruency. Whenever you hear the word congruent, um, it simply means that the shapes, they're identical. It means the corresponding sides are exactly the same. It's not the ratio now that we are investigating. No, the lengths are exactly the same, and also the corresponding angles, they're exactly the same. Okay, so congruence is, it's a type of similarity where the sides, they are exactly identical. Okay, and let's so there, this is now where you, if you were not listening beforehand, so this is where you start to listen now. If you have a scale area is what we're saying ratio. So a ratio of two sides, we say that it's a scale. It tells you for every one here, you're supposed to apply 10 units to the other factor or something like that. Okay, so it's called the scale. Okay, so the scale factor, let's say it's A over B. A over B simply means A is to B. This is the scale factor. Okay, so if let's say it's 2 over 1, it simply means 2 is to 1. This is a scale factor. So e.g. 2 over 1 equal to 2 is to 1. Okay, so you can actually write the scale factor ratio as a fraction or as in this ratio format. Okay, so when you're given this now, there is what we call area factor. See, you'll be dealing with a case of, for example, we had that those two, if you still remember, we had those two squares. So those two squares now, you can be asked, what's the area factor? The area factor is different than this one. This scale is called the linear factor. So this is linear factor, ratio of sides. But then the area factor is different. And how is it different? The area factor equals to the linear factor, this one. Then you square it. Okay, so it's actually equal to a squared is to b squared, like this. That means that you have to square the ratio. Okay, so you have to square. If you want the area factor, you have to take the linear factor and then you square. Similarly, if you have the area factor, you have to square root to get what? The linear factor. And there's what we call the volume factor as well. The volume factor, you have to cube. You have to cube what? The linear factor. Okay, so a cubed is to b cubed, like this. These are very important aspects that are tested in ZIMSEC maths. Okay, so take note of it. When you're given the scale, or sometimes you have to investigate for yourself, two corresponding sides, you have them. And then now the area factor, you square. And then when you're squaring, you're not squaring any individual number here. You're squaring everything. So this one, a over b squared, all in brackets, it simply means a squared over b squared, which is a squared is to b squared, like this. The volume factor would be a cubed over b cubed, like this. Okay, so these are important principles. So when you're given the volume factor, if you want to get the scale factor, you have to cube. You have to take the cube root, so that you get the a divided by b, like this. Okay, so this was just symbolic. It can be any number here. So when you're asked, a map is drawn to scale, you're given the scale here. They almost always give you in this format here, and then you're asked to calculate in centimeters, and then you're asked the corresponding one you're given in kilometers, or you're given in kilometers. You're asked to calculate in kilometers, and then the corresponding one you're given in centimeters. Take the smaller value, so the smaller unit for our case, it's centimeters. When you write this scale can be, you're allowed to put any units that you want there. Okay, as long as the units are the same. So you can put 1 kilometer is to 80,000 kilometers. But what I want you to do is you take the smaller scale, the smaller unit. So the smaller unit here, it's 1 centimeters, like this. 1 centimeter. And then you put on the left, you put on the right. what will have happened here is that, let's say you have 1 centimeter over 80,000 centimeters. These centimeters, they cancel. This is how you end up with 80,000. Okay, 1 is to 80,000. It's also the same thing if it were kilometers. It's also the same thing if it were meters. So you're very free to write whatever units that you want here. And the best way to, or the best units to use is to compare which units are mentioned in your question. So we make the centimeters and the kilometers. Check the smaller units. So in our case, it be centimeters. Only that. And then once you take the smaller units now, convert these ones to the desired bigger unit here. What would be the desired bigger unit? It'd be, so you'd need to convert this to centimeters first. To convert to centimeters, you divide by 100. Okay. So to convert meters, now you'll be now in meters if you divide by 100. To convert to kilometers, you have to divide by a further 1000. Okay. So what you're supposed to divide by here is what? So centimeters per kilometer. Okay. So here, what you're supposed to divide by is 100,000. Okay. If you are very lousy at dividing stuff, you can think of it this way. So it's 80,000 centimeters, then you divide by 100 centimeters, then you get what? This is also acceptable. Okay. Then you get 800. Then after getting 800 what? Meters. You've divided by centimeters here. Okay. So this is actually 100 centimeters per meter. So that's why you get 100 meters. Then you divide again by 1000 kilometers per meter. Then you get 0.800 like this, or 0.8 kilometers. So all these steps, these two steps, you can actually just do them in one step by just dividing here by 100,000. In other words, 1 kilometer is to 100,000 centimeters. Okay, so you use this, you divide by 100,000 centimeters per kilometer. What do you get? You get 0.8 kilometers. You now have a scale. The scale here, it's very important. You now have a scale that allows you to use to use simple proportion to convert to convert kilometers to centimeters. It's simple now. Okay, so now you can just say 5.6 centimeters. 5.6 kilometers, I mean, is to what? Is to more simple proportion. And then you end up saying 5.6 kilometers here divided by 0.8 kilometers here multiplied by 1 centimeter. Then obviously you divide, so you get 7. Okay, so 8 by 7, you actually get 56. So this was easy. So it's 50. You multiply both the upper part by 10. You multiply the lower part by 10. Then you get 56 over 8, which is what? Which is 7. 7 what? Centimeters. Okay. So again, what we did here was compare the units. You have centimeters and kilometers. Take the lower unit, centimeters, centimeters. After that, divide one side by 100,000 so that you can have this in kilometers. You now have a scale that you can use. Use simple proportion. You need 5.6 kilometers. This has got to be more. And then you flip, and then if it's more, bigger number on top, and then thereby you get 7 centimeters like this. And then you ask, calculate the actual area in square kilometers represented by a map of 100 centimeters squared. Okay, now you're dealing with square kilometers and square centimeters. You now need another area factor. So this one was the length factor, this one was the length scale. So you need an area scale. Well, how do you get it? It's simply 1 centimeters is to 0.8 kilometers like this. And then we say that for area factor, we have to square. And notice that when I'm squaring everything there. I'm not squaring just the units, I'm squaring also the number. So here you get what? 1 square centimeter is to what? 0.64, right? Square kilometers, like this. This one is your area factor. if it were volume, you would have cubed here. And here, 0.8 squared simply means 0.8 times 0.8. So you can even multiply this one separately. You get the same answer here. And then once you're done with this, now you say 100. You're now using simple proportion. Is to what? Is to more. If more, bigger number on top, and then you get 100 multiplied by this, then you get 64. 64 what? Square kilometers. Done. Okay. So just a recap. Here we now need the area factor. You don't go back here. You have something that you can work with, something that connects the centimeters to the kilometers. Repurpose that, square it, and then once you square it, you have this, and then you check more, and then if it's more, bigger number at the top, and then you do that simple proportion, you're done. Okay, this is a very common question. It comes almost every year. If it's not paper 1, then paper 2. Okay, so at least know this one. It's easy to score marks in this question. Okay, so that's it. Let's see. There's another question that we have to tackle. Yeah, so two similar cups have diameters 6 and 10. Already you're told that these are diameters. You're given two corresponding sides, which is great. And then the linear scale, because they want you to use, obviously, the concept of similarity. The linear scale would be what? 6 centimeters is to what? Is to 10 centimeters. So here I am saying smaller to bigger. So you're dealing with 3:5 like this. This is the linear scale, but then you're asked the ratio of the volumes. So the ratio of the volumes would be, you get the volume scale first. Okay, you can even say the volume scale is the ratio of the volumes. Okay, so to the power 3. Why? Because that's what we agreed upon. If you still remember when I was giving you an introduction to this, we were saying that volume, whenever you think of volume, it's cubic centimeters, cubic meters. Why? Because you're cubing the length vector. Okay, you're cubing the length scale. So this is our linear scale or length scale. So you have this, you have to cube it, and then once you cube it, now you get what? This is 3 cubed over 5 cubed. So you get 27 over what? Over 125, like this. This is your scale. Okay, I hope you understood it. So in the previous question, what we're having was we're having a case of areas. So that's why we had to square to get the area factor or the area scale. Here we're dealing with, if you want, you can even write 27 is to 125. It's still okay. Okay. So here we're dealing with volume. So you have to cube. Don't square, cube. Okay, that's the trick. So volume, remember, one way to remember it is that volume is a quantity where you need to multiply three measurements, okay, 3 lengths. So that's why we say cubic centimeters, cubic meters, cubic millimeters, and all those things. Just because we have 3 lengths involved. So it's also the same thing here. Length, the linear scale or linear, the length factor, it's only giving you the ratio of sides. So these sides we have to cube them so that we can get the volume ratio. And then given that the volume of the smaller cup is 100 cubic centimeters, calculate the volume of the larger cup. Okay, so here now you're dealing with a simple proportion. So it's 27 what? You can even say cubic centimeters here. Why? Because this is the unit that you're dealing with. Cubic centimeters. Okay, so which one is large? This one is small. Okay, so given that this volume of the smaller area of the smaller cup is 100, so this is 100. Okay, find the of the bigger. So bigger is supposed to be more, and then if it's more, it's what? Bigger number at the top. So you have 100 cubic centimeters here over 27 cubic centimeters here, multiplied by 125 cubic centimeters here. Okay, so then you just work it out. Okay, I'm sure you'll be able to find the answer. But then essentially what we're doing here was, just to recap, what we're doing here was we say that there's something called length area. Length area is usually, let's say, A over B. or A is to B, like this. This is length area. This is length scale. Or simply scale factor. Okay. So area factor would be equal to, or A squared is to B squared. And then the other trick that we talked about that you should watch out for is that you are squaring even the numbers as well. Okay, this is the area factor. And then we talked about A cubed over B cubed, or A cubed is to B cubed. This one is called the what? The volume factor. This one is called the volume factor. Okay. Then that's it. Okay, so yeah, that's it for this frequently asked questions. Yeah, so yeah, that's it. Thanks for watching. Make sure you like, share, and subscribe. Yuba out.